In this video, we're going to look at Maclaurin series or Maclaurin expansions. You have actually met some examples of this before. Last year, when you met the binomial expansion or the binomial theorem, you learnt that 1 plus x to the n was 1 plus nx plus nn minus 1 over 2 factorial x squared, etc., for any real number n. This series is only convergent if mod x is less than 1. Earlier, with complex numbers, we met Euler's relation, where e to the ix was equal to cos x plus I sin x. At that stage, we saw the Maclaurin expansions for sin x, for cos x, and e to the x. These are all convergent for any real numbers x. So in this video, we're going to look at the general case of the Maclaurin expansion or Maclaurin series. If we have any function f of x, then we can write f of x as f naught plus x f dash naught plus x squared over 2 factorial f double dash naught, etc. Whether this is convergent, for what range of values of x it's convergent, depends on the function f of x. We're going to prove this in exactly the same way that we showed that sin x was x minus x cubed over 3 factorial, etc. First of all, let's suppose that we can write f of x as a plus bx plus cx squared plus dx cubed plus ex to the 4, etc. And that this is an identity, not an equation. So this is going to be true for all values of x. In particular, let's put x equal to 0. f0 then is equal to a, and if you put x equal to 0, everything else is 0. Well, if these two are identical, if f of x is identical with the function this series expansion, then their derivatives should be the same. So if we differentiate, we will get that f dashed of x is equal to a differentiates to naught, b plus 2cx differentiating x cubed 3dx squared plus 4ex cubed, etc. Once again, we put x equal to naught. This gives us that f dashed naught must be equal to b. Everything else is 0. And we carry on in the same sort of way. We differentiate again, and we will get f double dashed x is equal to 2c, differentiating x gives 1, plus, and I choose to write this as 3 times 2 times dx plus 4 times 3 times ex squared, etc. Once again, put x equal to naught. F double dashed 0 now is going to be 2c. Everything else is 0. C, therefore, is equal to 1 over 2 f double dashed 0. And continuing in the same way, we differentiate again. That will give us f 3 dashes x is 3 times 2, I'm going to write 3 times 2 times 1 times d plus 4 times 3 times 2 times ex, and continue. Putting x equal to naught, we get f 1, 2, 3, 0 is, well, that is 3 factorial times d, and that gives us that d is 1 over 3 factorial times f triple dashed naught. In the same way, we can see if we carry on with this, If I was to differentiate again, I would have f4 dashes is 4 factorial times e. The pattern is just established and going to continue. 1 over 2 can be written as 1 over 2 factorial. And so similarly, e is equal to 1 over 4 factorial f4, 0. F, the next coefficient, is 1 over 5 factorial f5, 0, and so on. And if we substitute all these values back into the top, we get that f of x is equal to a is f of naught, plus b is f dashed of naught, so that's x f dashed naught, plus c is 1 over 2 f double dash naught, so cx squared is 1 over 2 times x squared times f double dash naught. The third one, dx cubed, that's x cubed times 1 over 3 factorial f triple dash naught, and so on. X to the 4 factorial f, fourth derivative, 0, and there we are. So that is Maclaurin's expansion, or Maclaurin's series. The convergence or otherwise, as I mentioned earlier, depends on the choice of the function f. Now let's look at a function that we haven't seen before. Express log 1 plus x as an infinite series in ascending powers of x. Well, we're going to use Maclaurin's series for this. So we take f of x as log 1 plus x. We're going to need f naught, f dash naught, f double dash naught, etc. to fill in the gaps in the series. So let's go first of all for f naught. f0 is log 1, which is 0. The next thing we need is f dashed x. F dashed x, if I differentiate log 1 plus x, I get 1 over 1 plus x. And that tells me that f dashed 0 is 1 over 1 plus 0. It's just 1. Differentiate again. You might prefer to see this written as minus 1 plus x to the minus 2. I was differentiating 1 plus x to the minus 1 minus 1 plus x to the minus 2. This gives us f double dashed 0 is minus, put x equal to 1, it's just minus 1. f3 dashes x, differentiate again. It's going to be minus minus, so that's plus 2, 1 plus x to the minus 3. That tells me that f triple dashed naught is 2. Put x equal to naught. Differentiate again. We just need to make sure that we know what the pattern is. Minus 3 times 2, which I'm going to write as 3 times 2, 1 plus x to the minus 4. That gives me that f4, 0 is minus 3 times 2. One more, I think, just to make sure that we can really see what's going on. Bringing the minus 4 down gives me plus 4 times 3 times 2, 1 plus x to the minus 5. That tells me that f5, 0 is plus 4 times 3 times 2. So we should be able to see what's happening. Firstly, the sign is alternating, plus, minus, plus, minus, plus. Then we go 1. I can write that as 2 times 1 if I wanted to. This is 3 times 2. This is 4 times 3 times 2. The next one is going to be 5 times 4 times 3 times 2. And so if we put this into the general formula here, we get that f of x is equal to f of naught, that's 0, plus x f dashed naught. F dashed naught is 1, plus x squared over 2 factorial times f double dashed naught is minus 1, plus x cubed over 3 factorial times f triple dashed is 2, plus x to the 4 over 4 factorial, and f4 dashes is minus 3 times 2, plus x to the 5 over 5 factorial, and f5 is plus 4 times 3 times 2, and so on. Give myself a little bit more space. 0 we can forget about. X. I've now got minus x squared over 2. I've now got plus x cubed. 2 cancels, leaving just 3 on the bottom. I've now got minus 3 times 2 cancels, leaving me with 4 on the bottom. Plus 4 times 3 times 2 cancels, leaving me with 5 on the bottom. Now we have a very clear pattern and we can see what's going on. So this now is log 1 plus x. Is it any use? In other words, does it converge? This converges when minus 1 is less than x is less than or equal to 1. So it's useful within that range. If x is outside that range, then it will not give a good approximation for log 1 plus x.